We've now talked about a number of discrete random variables, and so next we'll talk about continuous random variables. We already did one example of this before. We talked about the spinning arrow, the kid's little spinner that you flick and you point at a random angle. And we said that spinner had a final angle that was between 0 and 2 pi, and that angle we called theta. That was random, and the important distinction here is that unlike the discrete random variables that we saw, the outcomes are not a finite or countable set of things. There's an uncountably infinite number of angles theta that you could take. So for that, because of that, we say that that random variable theta, the angle is continuous because it varies in a continuous way, right? It's not like you have dice and the outcome is, the numbers 2 through 12. It's not like you're flipping a coin and the outcomes are heads or tails. The outcome is some random angle, and if you were to take a decimal expansion of that, it would go on forever. So in this particular case with the spinner, we would say that that angle varies uniformly because whatever angle you happen to be pointing at is equally likely. Okay, it's not like the spinner has some weight to it so that it points more in one direction or another. That's a particular attribute of this particular distribution, right? In general, quantities are not going to be varying uniformly like that, and that'll be the focus of this lecture here. So we talked about a probability mass function, a PMF, which was this step function, or a stem function, I should say, that talked about how likely the various outcomes are for a discrete random variable, right? We said if you're rolling 2 dice, the PMF tells you the probability of getting 2 or 3 or 4, and so on and so forth. When you have a continuous random variable, what you have instead is something called a probability density function, or PDF. And a PDF is defined in terms of integrals. And so the property of a PDF works like this. The defining feature of a PDF, of a density function, is that if you have this underlying random variable x, then the probability that x lies between a and b, two fixed endpoints, the probability that it lies between these two endpoints is this integral here. It's the integral from a to b of this density function f of x. So in other words, f of x is this function that is associated with a random variable that satisfies this property. Okay, I've drawn a picture of it here, right? If this is my PDF, this sort of humped function here, then the probability that the random variable lies between a and b, these two values, is just all this stuff in this shaded region here. So what obviously has to be true about f? Well, of course, f of x has to be greater than or equal to 0 because you can't have negative probabilities anywhere. And the random variable x has to lie somewhere in these real numbers. If I take the integral of the PDF from plus negative infinity to positive infinity, it has to integrate to 1, right? The integral of the whole function has to be 1 because probabilities have to sum to 1, and that's what's going on there. Here's a point that confuses a lot of people, and it's unfortunate because you'd need to take a lot of measure theoretic type instruction to sort of make sense of this, which is not something we're going to cover. But here's the question that conceptually we'll address this question by, we'll address this issue by looking at the question that I have written up here, which is what is the probability that a continuous random variable x will take on a specific value x naught? Okay, so in that example with the spinner, I could ask, what's the probability that if I flick this spinner and it goes spinning around like this, what is the probability that it points at exactly 45 degrees? Right, not 44, not 46, not 44.0001, but exactly 45 degrees. What is the probability that it's pointing at that kind of angle? Well, I think we can agree intuitively, or we can agree that logically, intuitively, whatever kind of word you want to use, that's got to be 0. It's got to be 0 because the probability of any particular one of these outcomes happening exactly is going to be 0. And you can verify that that's true, or you can verify that a PDF obeys this property because you could say, well, what is the probability that x is equal to x naught like this? What is the probability that it's equal to this value? Well, that's the probability that the random variable x lies in this interval here. It's greater than or equal to x naught, and it's less than or equal to x naught. So that's just an integral of the PDF from x naught to x naught, and of course that's 0, right? Take an integral from, where the domain of integration is length 0, and you get 0. So yeah, cool. A PDF satisfies this property that we want it to satisfy. What this tells us is that we don't actually care about the values that this function f of x takes. We only care about the integrals. So if I give you the values of the function itself, that doesn't actually tell us anything meaningful. If I tell you that f of x is equal to 17 somewhere, I say, oh yeah, f of x is equal to 17, that doesn't actually give you any information because it doesn't tell you anything about probabilities. The only way you can work out any probabilistic information is through the integrals. Okay, so I'll say it again. You don't care about the values of the PDF. The function itself is not important to you. What is important to you is these integrals. So you only care about f of x. You only care about this PDF to the extent that you can take integrals of it. That is the only useful information you can get. As engineers, the actual minutiae of this are not something we have to worry about because we care about actually building things and actually making things that work. And in the real world, the sort of complexities or intricacies of this kind of argument don't really come up. As I may have mentioned before, if you use measure theory, you can kind of unify this notion of a continuous versus a discrete probability distribution. They're all just special cases of what are called a Borel or a Lebesgue measure. But you don't have to care about that at all. We're not mathematicians, we are engineers. You remember we defined something called a cumulative distribution function? For a discrete random variable, we defined this already. And what is a cumulative distribution function? Well, it's a function that we call capital F of x, which is the probability that your random variable is less than or equal to x. So if you're rolling some dice, f of 9 would be the probability that the dice have a number that's less than or equal to 9. The PMF, by the way, would be little f of 9 would be the probability that you get exactly 9. In fact, I'll write that down just to make sure we don't forget that for rolling 2 dice. 2 dice, if that shows up. We would say that the CDF would say f of 9, and that's a totally arbitrary number, is the probability of rolling at most 9. And the PDF, little f of 9, that is the probability of rolling exactly 9. Okay, that's the difference between the PDF and the CDF. So we define this thing, and how do you compute that? Well, it's pretty straightforward. You say the probability that the random variable takes on a value less than or equal to little x. Well, it's just a sum of the PMF for all values less than x, right? How do I compute this thing? I'll draw that. Stem plot here. If this is my, I'll draw it really quick. So for dice, it's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you would do that stem plot there, which I'll hack through really quickly here. I don't think I left myself enough room, just barely. I did good, like that. And so how would I compute f of 9? How would I compute that? Well, I would take 9, and I would just add up all of these probabilities to the left of that. Right? I would add up all of these little ones here, and I'd compute, and I'd get whatever I get. But it's a summation is the point I want to make here. You add up the probabilities that are less than or equal to you. Okay? Now, for a continuous random variable, instead of taking a sum, you just take an integral. Right? You have a continuous quantity now, so you can't sum things up. You just take an integral. And so what is the picture that you'd have there? Well, if I have a PDF, like say that, and I want to know the f the value little f, sorry, let me be more clear. If I want the CDF evaluated at this particular value, I would just compute this integral here of everything lying to the left like that. Hopefully that shows up. And that's how that works. You compute, just integrate everything that lies to the left, and that integral is what the CDF is. Let's go back to that spinner example now with a uniform distribution. For that spinner example with angle theta, let's determine the PDF, the CDF, and the probability that the angle is between 0 and pi on 3. Not very interesting. You can work this one out. There's not a lot of algebra that goes into that. The PDF looks like this. F of theta, your PDF, it's equal to, well, a couple of points on this. The PDF is only defined for theta between 0 and 2 pi, right? It's not defined for anything outside of that because those are the only values we're saying that the spinner could take. Could I have done this from 0 to 360? Sure, if I wanted to measure things in degrees instead of radians, but we'll stick with radians. Okay, so the PDF is 1 on 2 pi for an angle from 0 to 2 pi, and it's 0 otherwise. Let me draw a picture of that here. Here's the x, or the theta axis, I should say. So it looks like that. And then this is the probability axis like that. And what I'm saying here is that if I wanted to draw the probability density function, if this is 0 and this is 2 pi, then that density function is 0 everywhere down here, and then, or it's 0 down here. Let me just, I've already drawn the axis, so I'm drawing this part in there. And then I'll do the line over here. It's flat from 0 to 2 pi, and it's a flat line because it's constant, and then it goes back to be nothing like that. In fact, let me draw that again. It looks like this. Very quick. You got 0, you got 2 pi, and the PDF just looks like that. Okay, that's all I really want to communicate here. It's a function that goes up, and this particular value there is 1 on 2 pi. Now, where did I get that number from? Where did 1 on 2 pi come from? Well, it came from the fact that I need this integral here. I need this integral to be equal to 1, right? I need the total integral of a PDF has to be 1, and therefore the volume, the mass under this line here has to be 1. And the only way that can happen is if the probability value here is 1 over 2 pi. Okay, because you're ranging theta is going from 0 to 2 pi in the horizontal direction, and so the vertical direction you go on a 1 over 2 pi instead, like that. So that's the PDF for that spinner. The CDF, assuming that theta is between 0 and 2 pi, the CDF is just the integral of the PDF. That's always true. You can always compute a CDF that way. So the CDF is just the integral from minus infinity to theta of f of t dt. So what is that? It's the integral from, because this PDF is only defined from 0 to 2 pi, that's the same as taking the integral from 0 to theta of 1 on 2 pi dt, which is theta on 2 pi. Okay, so what does the CDF look like? The CDF looks like this. I should make a little note here. This is the PDF. And then the CDF looks like the following. I'll do the same, just a line there. I'll do, this is 0, and this is 2 pi. And then the CDF, it's 0 like that, because of course, there's no way that the spinner can be pointing in something negative. And then it goes from 0, it increases at a linear rate up until 2 pi, at which point it gets the value of 1. So this is 0, this is y equals 1 up there, at which point it remains constant throughout. So that's what the CDF looks like. It's flat, and then it's flat, and then it moves up in a linear fashion, and then it moves like that. That's the CDF. And so that's algebraically what that expression works out to be. And then finally, we're asked for what is the probability that theta lies between 0 and pi on 3, and so we'll work that out. By the first two parts, what is the probability that theta is between 0 and pi on 3? Well, it's just the integral of the PDF, which is the PDF which we already established is just 1 on 2 pi. So you integrate that from 0 to pi on 3, and you get 1/6. Okay, it's the world's simplest integral there. There's nothing that I really did. I just integrated the PDF from 0 to pi on 3. And in that picture I drew here, that just turns out to be integrating 0 to, and now I know I'm filling up this diagram quite a bit, but pi on 3 would be about, pi on 3 is like over here, so it's hard to see, so I'll do some cross-hatching in the other direction. That's just me taking this integral right there. I hope you can see that. The integral of that little piece there. So that's what that is. Now, just as we have certain discrete random variables that are very useful to us, Bernoulli, binomial, Poisson, and so on and so forth, there are also certain very useful continuous random variables that are useful to us, and we give them names. And so we'll describe a few of those now. You've got the uniform distribution, which in fact we just looked at, the exponential distribution, the gamma distribution, and the normal distribution. There are plenty of other distributions out there, but these are the ones we're really going to focus on. The uniform distribution is the same as the spinor example that I just gave. It occurs when all of the outcomes for the random variable are equally likely. Okay, and the way we write that is we say x, the random variable, we write a little twiddle sign there, x twiddle u for uniform, a comma b. That says that all of the values are equally likely to happen between a and b. The PDF, which you just saw a moment ago, is just 1 over b minus a, which is a constant. And I should clarify that it's actually f of x is equal to 1 on b minus a, provided that x is between a and b. So let me make a note of that here. Actually, it should be f of x, it's 1 on b minus a if x is between a and b, and it is 0 otherwise. That second bit there, the fact that it's 0 otherwise, that's usually kind of a given, right? We know that, we're comfortable with that sort of thing. So often one doesn't write that. And I forgot to write it in that slide there because it just didn't really matter to me much at the time. So that's the PDF. Again, we already worked this out for the spinor example. The spinor example is the special case of a uniform distribution where a is 0 and b is 2 pi. Okay, so all we're doing is generalizing that to any other interval we like. The CDF is just the integral of the PDF, so it's this thing here, x minus a on the quantity b minus a, and the spinor example, as I just wrote, had a equal to 0 and b is equal to 2 pi. Here's an example that shows that a linear change of variables does not change whether a random variable is uniform or not. So we're going to show that if x is a uniform random variable from a to b, then if I take c times x plus d, so a linear function of x, if I take c times x plus d, then that is also uniform. But now it's uniform on the intervals c times a plus d and c times b plus d. So for example, if I took that spinor, remember the spinor before was uniform from 0 to 2 pi, and instead I take the spinor and I multiply it by 17 and I add 312, we want to show that that resulting outcome is still uniform, but it's uniform on this different interval now, right? From 312 to, whatever 17 times 2 pi plus 312 might be. So how does that work? This kind of question tends to scare people a lot, or it confuses them. The way you would analyze this is a tricky thing. Here's, in fact, I would say the following. A kind of question that people get really confused with in this subject a lot is a question that says, prove this random variable has a certain form, or show that this random variable has this certain form. I don't like to use the word prove. People don't know how to handle it. How do you do that? How does that kind of argument look, where I say, here's a random variable, show that it has this kind of distribution? I would say that almost always the way you're going to want to go about this is to look at the CDF. Okay, whenever I tell you, show that this kind of random variable has this kind of distribution, what I almost always mean is calculate the CDF of the random variable we're interested in, and then show that the CDF has the form that we're looking for. This argument, when you see it the first time, is probably going to confuse you a little bit. It won't after we go through a lot more examples, which is something we are going to do. So first of all, let's say, what is the CDF? What we want to do, first of all, we want to prove that this quantity here, Cx plus D, we want to prove that that quantity is a uniform random variable on this interval. Okay, Ca plus D and Ca plus D and Cb plus D. We want to prove that. And so we'd say, well, what is the CDF for a uniform random variable on this interval, right? What is it? Well, we could just go back to the slides and we'd say, well, the CDF for that kind of distribution is it would look like this, okay? If y follows a uniform random distribution, then this would be the CDF, okay? So we'll just make that note. So we'll say this is the CDF that we want to obtain, right? We're trying to prove that this random variable Cx plus D has this CDF. If I can do that, then I'm done. Okay, so now I've written down what the target is, or what the thing is going to be that we're going to try to get this variable to match up with. And so what can we say? So let's suppose that y is between Ca plus D and Cb plus D. And we'll say, okay, what is the probability that Cx plus D is less than or equal to y? Okay, now this is me saying, let's look at Cx plus D, and let's look at the CDF for that thing, and show that the CDF of Cx plus D is equal to this thing here, which I just circled a moment ago, right? How do I do that? So let's say, okay, take any value y and say, what's the probability that Cx plus D is less than or equal to y? Well, all I've done here from the one step to the next is I've just rearranged, I've just done some algebra, right? I took this inside expression here. I said Cx plus D is less than or equal to y, and I've just rearranged that expression in terms of x, that's all. Okay, and what is the significance of me doing this? Let me erase those bit there. Okay, what is the significance of me rewriting that this way? I've now got x is less than or equal to quantity y minus d on c. Well, I've got an x over this side here. This is saying, what's the probability that x is less than or equal to this thing? Well, what is that? That is the value for the CDF for x evaluated at this point. Okay, so I should say I evaluate the CDF for x at this point, and if I go back to the CDF for x, I'd see it's, and again, this is a place where I should skip back and show you where this expression comes from, or rather how I get this thing. And let me do that now. I'll just skip back to the definition of a uniform random variable. I'm going to skip back really quick and then show you that expression, which I want you to lock into your brain. So the CDF for a uniform random variable from a to b is this thing here, x minus a on b minus a. Okay, when you evaluate the CDF at a point x, it's that x minus a and then that divided by b minus a. And now we'll skip back to these calculations I was doing. And now what I did is I said, well, I'm evaluating the CDF at this point here, y minus d on c. And so I do a y minus d on c like that, and then minus a, and then on b minus a. This is me just plugging in this value, y minus d on c, into the CDF. Okay, and then once I do that, I'll erase all this stuff again. Once I do that, and I work out the algebra, I get exactly this expression here, which turns out to be the CDF f of y, which is indeed a proof. If you had difficulty following that, don't worry, we're going to go through a lot more examples like this. This is the simplest example where you're proving that a certain kind of random variable has a certain distributional form, and I just want you to see how those kinds of proof sketches work. But I don't expect this to be completely clear just yet. We have a lot of ways to go. Let's do another example here. You've got a sequence, x1 through x5, of independent uniform random variables, and each one of these samples is between 1 and 5. Okay, so let's draw the PDF just for fun. Here's 1, and here's 5. Here's 1, and here's 5. And then what does that PDF look like? Well, it's 0 for a while, and then it jumps up to 1/4 for a little bit, and then it goes back down like that, right? That's my, and then this would be, x equals 0 there. That's the y-axis. Okay, and so we take a bunch of sequences. So we take a bunch of samples that lie, somewhere in here, and we want to know what is the probability that exactly 3 samples are at most 2. Okay, so we're sampling these things. They're 1, 2, 3, 4, 5, and we're making uniform samples, so they lie anywhere in this piece here, in this interval from 1 to 5. And we want to know what's the probability that exactly 3 of them are at most 2. So how could that happen? Well, this ends up being an interesting example where we need to talk both about a uniform distribution and a binomial distribution. So where does a binomial distribution come from? So let's ask this. What's the probability that any one of these samples, remember I'm taking 5 samples and each of one of them lies between 1 and 5. And I want to know what is the probability that any one sample is at most 2. Well, what is that? Well, that's just evaluating the CDF for a uniform distribution at the point 2, and that's 1 in 4. So this is the same as if I took 5 samples of a Bernoulli random variable where the probability of success was 1/4, and I want to know the probability that I have exactly 3 successes, right? So what have I done? I started with talking about a sequence of 5 independent uniform random variables. And I said, well, for each one of those random variables, I'm just interested in whether that uniform random variable is at most 2. And I just said, well, the probability that any one of those samples, if I take any sample, I say the probability you're at most 2, that's 1/4. So what am I really doing? Each one of these 5 samples I'm taking, I've got a probability 1 in 4 of success. And so this example is asking me to say, what's the probability that I have exactly 3 successes? Well, that, if you remember your discrete random variables, that's a binomial distribution, or a binomial random variable. And the parameters now are n equals 5 because you have 5 attempts, and then p is equal to 1/4 because each attempt succeeds with probability 1 in 4. And so you just plug in the binomial distribution and you get 0.0879. So that's the probability of that. So we use these uniform random variables as like a vehicle to also look at binomial random variables. So just an aside about uniform random variables, a little bit of terminology. A uniform random variable that lies between 0 and 1, we say that's standard. Okay, and one thing you'll notice is that if x is uniform between a and b, then if I just subtract a and divide by b minus a, I get something that is uniform between 0 and 1. And so therefore, any uniform random variable is just a linear transformation away from being uniform from 0 to 1. So oftentimes you just talk about random variables as being uniform random variables as living between 0 and 1, and then you do the scaling afterwards. So anyway, terminology point there, that's all. Turns out that for any positive value lambda, this thing here is a valid PDF. So it's f of x, it's lambda times e to the power of minus lambda x for positive values of x, and then 0 otherwise. That is called an exponential distribution, and its CDF looks like this. Again, the CDF by definition is just the integral of the PDF, and it's 1 minus e to the power of minus lambda x. Here's what the PDF looks like, the exponential distribution, for various values of lambda. So you'll notice that for high values of lambda, you have this distribution that decays really, really quickly and shoots on down, whereas for lower values of lambda, like the orange one there, you have something decaying slightly more slowly, although it's still at an exponential rate. So that's called an exponential distribution, defined for all positive values of x. The exponential distribution also gives rise to the gamma distribution, which is just the sum of a bunch of exponential random variables. So if I take a random variable which is just the sum of k exponential random variables, each having the same parameter lambda, we'd say that variable follows a gamma distribution, and its PDF is this ridiculous, messy thing here, which you do not need to memorize. I don't have it memorized, so you certainly don't have to. You've got this capital gamma here, gamma of k. Gamma is the gamma function, which is the factorial function for integer values, and it's this weird-looking integral in general. Again, don't worry about that function either. Basically, it means factorial. That's all you need to worry about. Factorial of the input minus 1. When k is equal to 1, then f of x is just an exponential distribution. That's point one to make, that the exponential distribution is a special case of the gamma distribution where k is equal to 1 by definition. What's also kind of neat is that you can even, I don't think we're actually going to use this fact ever, but it is worth knowing that the gamma distribution is defined even when k is not an integer. Okay, it's defined because the gamma function here is defined for non-integer values. So I don't know why I don't know why that would ever come up in the course, but it is a true fact about the gamma random variables, and so that's worth knowing. There isn't a closed form expression for the CDF. Okay, I don't have something nice to write there. It's just defined as the integral of the PDF, but there isn't anything nice to be written there. Here's what the gamma distribution looks like. So when k is equal to 1, as I mentioned before, the distribution is just an exponential distribution, as you can see like this. On the other hand, when k is equal to 5 and k equals 8, you get sort of more of a bell-type shape like that. That's 5 and that's 8 like that. So it tends to have kind of a hump to it, but that's what that looks like. The normal distribution, also known as the Gaussian distribution, you've probably seen this. It has a PDF given by this thing. It depends on two parameters, mu and sigma squared. Sigma is typically required to be positive. We would write that as x and then a tilde and then the letter n for normal and then mu and sigma squared. Normal distributions are preserved under linear transformations. So if x follows a normal distribution with mean mu and variance sigma squared, then if I take ax plus b, so multiply x by a and add b to it, that's also normal with a new mean, a mu plus b, and then the variance is a squared sigma squared. The special case where mu is 0 and the variance is 1 is called a standard normal distribution. And there, as you may know, there is no closed form for the CDF. So that's all we have to say about that. Normal distribution looks like a bell curve, right? It's these things over here. You've seen normal distributions before many times, so I don't have a lot to say about those. Some sanity checks here, just to remember the terminology. PMF, probability mass function, that is something that only exists for discrete random variables. And that is for telling me what is the probability that the random variable takes this particular value. Again, you're rolling dice. The PMF tells me what's the probability that I roll a 7. The counterpart for that with continuous random variables is the PDF, the probability density function. And what that is for is it says the probability that my random variable lies between A and B is this integral. The CDF actually applies to both of those. That is a concept that works just fine for both discrete and continuous random variables. The CDF is just the f of x is the probability that the random variable is less than or equal to x. That's sanity check number 1. Sanity check number 2 would be a little a matching game. If you're watching this asynchronously, it would be a good time to pause and try working through these yourself. I will go ahead and do that now. I think I'll do this by matching, I guess we'll look at things on the left and look at things on the right. So a Bernoulli distribution, I can tell you, is the world's simplest random variable, which takes only 2 values. I would say the binomial distribution is the sum of a fixed number of Bernoulli random variables. A geometric random variable is the number of Bernoulli trials until your first success. A Poisson random variable involves a low probability of success but many attempts. If you remember that, we define the Poisson random variable as being a limiting case of a binomial distribution. Uniform random variable is the world's simplest continuous random variable. Exponential random variable would be a I guess this is the weakest one of these. It's a rapidly decaying continuous random variable, although a lot of these are, or a gamma distribution also rapidly decays, so that's kind of a judgment call. A gamma distribution is a sum of exponential random variables, and then a normal distribution is a nice smooth continuous bell curve. So that's the answers to that quiz there. Here's an example of another PDF that we'll construct that's motivated by a question or a post that came up on Reddit a while back, I think under the Data is Beautiful subreddit. And the statement looked like this. They said, for real world data, the number 1, is by far the most common first digit. And we've got an example of this here where I've gotten a bunch of countries and I've written down their populations. Again, this is from that post. They took a bunch of countries, took their populations, and wrote down the leftmost digit. So for example, the UK and Thailand, their leftmost digit is a 6 because they have a population of about 60 million. And so for UK and Thailand, you record the number 6. That's because 6 is the leftmost digit there. Whereas then Egypt, and the Philippines, Ethiopia, Japan, if I go a little further down the list, they all have a leftmost digit that is the number 1. Okay, and so what they did in this post is they took all those countries, they wrote down the populations, and they took the leftmost digit, and they recorded how many times each of those digits appeared. And that's what you see in this sort of histogram or bar chart over there. And the thing that jumps out is that, wow, the number 1 appears a lot more than the number 2, which appears a lot more than the number 3, and that you have this sort of decaying thing happening here. So 1s and 2s and 3s are a lot more common than 6s, 7s, 8s. If you just go through the populations, if you have a book, an almanac or whatever, the populations of all the countries in the world, and you look at the leftmost digit, you'll see the number 1 appears a lot more than the other digits. And this isn't just true for population. This isn't some screwy thing about that. It's true if you look at like the sizes of lakes, or if you grab a book of scientific constants like, pi and E and Planck's constants and Avogadro's number and all that stuff. If you grab a book of those, it's still even true there. Like the number 1 appears a lot more often. So it's just this bizarre thing that happens to happen. I said that poorly. It's a bizarre phenomenon. And so we'll try and explain where the heck that comes from. It doesn't work with things like phone numbers, not surprisingly. There are specific criteria that need to hold true, and so we're going to look at exactly what those are. So the way the statement was written in the post was that they said for real-world data, 1 is by far the most common first digit. So that requires some clarification or some conditions here. So what actually has to hold is that you have to be holding data sets that vary over many orders of magnitude, meaning that you have a data set where some of the entries have only 2 digits, some of them have 3, 4, 5, 6, where the values can range over many orders of magnitude. Of course, population satisfies this because the largest countries in the world have populations in the billions, whereas the smaller countries might not even have populations in the millions, right? They might even only be in the thousands. So that is data that ranges over many orders of magnitude. The other examples I gave, scientific constants, of course, range all over the place, right? You 10 to the 23 for Avogadro's number, and then the Planck's constant is 10 to the minus 60 or something ridiculous like that. So those certainly satisfy that condition. Sizes of lakes certainly satisfy that condition too. You've got gigantic lakes, you've got tiny lakes. Their sizes vary over many orders of magnitude. So what we're going to say is a statement that's a little more precise. We're going to say that data sets that vary over many orders of magnitude have this property that the digit 1 appears in the leftmost entry the most. That doesn't explain why this happens. It's still bizarre, right? So how could we work this out? Well, we could say the number of digits in a number is basically the log base 10 of that number. Right? It's basically equal to that, rounded down. I mean, it is exactly log base 10 of x rounded down. So we'll forget about the rounding just to make things easy for ourselves. So if I tell you that a data set ranges over many orders of magnitude, like it ranges from 10 to 10 billion, or 10 or 1 billion, I think is the example we're doing here, what I'm effectively saying is that the log of that quantity follows a uniform distribution. Okay, if we say the number of digits follows a uniform distribution, like whether you have 1 digit or 2 or 3 or 4 or 5, if the number of digits follows a uniform distribution, that's basically the same as me saying that the log base 10 of the random variable follows a uniform distribution. And so in this particular case, we'll make things easy for ourselves. We'll say that, let's assume that for world populations, basically the number of digits follows a uniform distribution between 0 and 9. So roughly between 1 and 1 billion. Again, a crude simplification here just to sort of get the point across, right? So we'll say, okay, now we've got a random variable x such that log base 10 of x follows a uniform distribution between 0 and 9. Okay, we started with the statement x varies over many orders of magnitude, and we sort of manipulated that statement into something a little more concrete, which is that, okay, log base 10 of x, we're going to say that follows a uniform distribution between 0 and 9. Okay, so now what are we going to do? We've said log base 10 of x follows a uniform distribution between 0 and 9. So let's compute the PDF or the CDF for x. So how does that work? Well, we'll say, okay, we know that log base 10 of x follows a uniform distribution. And so therefore, a uniform distribution between 0 and 9. And therefore, the probability that log base 10 of x is less than or equal to t is going to be t on 9. That's just me plugging in the PDF for a uniform distribution. Okay, so now what do? I'll say, well, log base 10 of x is less than or equal to t. That is the same thing as me saying, remember the rules for logs where you bring the base of the log out and that now becomes the base of an exponent. That's the same thing as me saying x is less than or equal to 10 to the t. So therefore, the probability that x is less than or equal to 10 to the t is t on 9. And so therefore, what is true? Therefore, the CDF for x is log base 10 of x on 9. And therefore, the PDF for x, which I get by differentiating the CDF, is this thing here, 1 on 9x times the natural log of 10, which is about 0.048 on x. Okay, and so what have I done? I've now gotten a PDF for this random variable x, which is supposed to represent the populations of a country, the random population of a country sampled from the Earth. And so what is the proportion of samples where the leading digit is 1? Well, what do you get? You have to integrate x goes from 1 to 2, and you go from x ranges from 10 to 20, and 100 to 200, and so on and so forth up to 10 to the 9 and 2 times 10 to the 9, and that ends up being 0.30. Okay, so that's how that works. Again, it's a fun example. Doesn't really have a concrete purpose other than an attempt to explain this thing, which is called Benford's law. So you might see that in other places too. Let's next talk about expectation. Distribution functions are a means of describing a phenomenon from a probabilistic standpoint, right? When I say distribution functions, I mean PDFs, PMFs, and CDFs, right? It's me giving you a function that describes the behavior of a random variable. Oftentimes in the real world, we don't know or we don't care about the actual distribution function, but we just want to characterize it by means of a few parameters, right? If you've ever had a boss tell you, just give me a number, you can relate to this, right? You don't want to know the exact way the distribution function behaves. You just want some basic numbers, some simple numbers that make things easy for you. You measure the temperature in a room, right? It might vary throughout the day. It's 75.3 now, and then it's 76.1, and then 74.7, and so on and so forth, right? Do we really need this sort of PDF that describes temperature? Well, no. What would you actually do in the real world? Well, you just take these numbers and average them together, right? We call that, in probability, we call an average an expected value. So that's the expected value of that experiment. It would be if I were to take the measurements of the temperature in a room and average those and report that value. So the motivation is as follows. So you make observations of a random variable x. You take a bunch of experiments, and you have a bunch of different samples of this random variable, x1 through xn. And the expected value of x is defined as being just the geometric or the arithmetic mean of these things. So x1 summed through xn divided by n. And the expected value of x is defined as the limit as n goes to infinity of this sum. And it's kind of weird. This is not going to be something we're going to focus on in this course, but it is kind of weird that I'm talking about a limit here for a quantity that is random, right? It is not obvious that that limit even exists. And the fact that it does exist is what's called the law of large numbers, so which was beyond the scope of this course, but you'll have to just accept that that is true, that in fact this limit does exist, randomness notwithstanding. So computing expectation for both discrete and continuous random variables is pretty simple. If you have a discrete sample space with n events, and pi is the probability that event I occurs, some basic analysis of linearity of taking limits works out that the expected value of x is just the sum of the probabilities times the values of that random variable. So we'll do an example of that to clear this up. For a continuous random variable, you just replace that sum with an integral. So the expected value of a random variable, of a continuous random variable, is the integral of x times the PDF. And an important note, conceptual note, is that this expression e of x, it's a deterministic quantity, right? It is not random. It's a number. I give you, I say there's a random variable with a certain kind of distribution. The expected value, it's a number that you write down. It's not random. It's not like flipping a coin where the outcome depends on the experiment. Nope, expected value is just one single value. So we'll do some examples of this in a minute. You can also take the expected value of a function of a random variable. Okay, if I have some function, g of x, then the expected value of that function would be the sum of the probabilities times that function evaluated at those entries. Again, this confuses people a lot. It's a really important point, so we're going to do an example of this in a minute. This is often a sticking point for people, so look at this very carefully. For the continuous case, the expected value of a function of a random variable is just the integral of that function times the PDF. So let's do some examples to make this a little more clear. If you roll a six-sided die, just one single six-sided die, the expected value is as follows. So all of the outcomes on a die have an equal likelihood of happening. They're all 1/6. So I take 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6, which is 7/2. Okay, 3.5. Now let's say I roll a single six-sided die, and I square the result. Okay, so I get a number 1 through 6, and I square it. So then I get either 1, 4, 9, 16, 25, or 36. The expected value of x squared is there's a 1/6 probability of getting 1, a 1/6 probability of getting 4, a 1/6 probability of getting 9, 1/6 of 16, of 25, and 36, and I get 91 on 6. Okay, that's the expected value of the square of the value on a die. For a random variable x, if the PDF is this thing, f of x is square root of 4 on pi minus x squared for 0 from x ranging from 0 to 2 on root pi. Where did I come up with that PDF? I sat around and goofed around with either Maple or Wolfram Alpha for a while until I found a non-negative function that happens to integrate to 1. So that's just the most arbitrary, goofy-looking function I could come up with that would satisfy the necessary conditions for a PDF. So let's just take this PDF, for example. What is the expected value there? Well, what do? You integrate. And as I said up there, that we define this PDF just for x between 0 and 2 on root pi. And so the expected value is the integral from 0 to 2 on root pi of x times the PDF, and then ends up being on 8 on 3 pi to the 3/2 for whatever that's worth. For that spinner example, where you're flicking that spinner and you have the needle pointing in some direction, we could ask, what is the average distance from the spinner to the x-axis? And what do I mean by this? I mean, if I have my spinner here like that, and here's my coordinate axes, and let's say my spinner is pointing in this direction, like that, I could ask you, what is this distance here? And let's assume this is the unit circle, by the way, on unit circle, because that would make a difference, of course. So we'll say, what is the average distance from the spinner to the x-axis? which is, oh, sorry, no, that's the y-axis, so forget that. The distance to the x-axis, which is this one down there, right? What is this typical, what is the average distance here, this thing? Okay, that'll be something we'll try and calculate. What is that average distance? So what is that? So that distance, I don't think it's too hard to convince yourself that that is the absolute value of the sine of the angle, right? In fact, this picture I just drew looks like it's straight out of a trig course, right? That literally the definition of the sine of an angle is just the y position on the unit circle, and so I'll take absolute value because we're measuring distance. Expected value of absolute value of sine theta. If you work out that integral, you'll get 2 on pi. So that's how that works. Linearity of expectation. This is a cool trick that you can get a lot of mileage out of. You'd be surprised how often this comes up and how often it makes people's lives a lot simpler. So expectation is always a linear operator, which means that the expected value of ax plus b is equal to a times the expected value of x plus b. And in particular, a place where this happens a lot is that expectations of sums are equal to sums of expectations. You are going to be doing this step here. This is going to happen a lot in this course. The expected value of the sum of a bunch of things is equal to the sum of those expectations, right? This expression on the right looks easier, doesn't it? Because it's the sum of a bunch of separate expectations. Expectation with a bunch of things inside it, not so much fun, right? So anytime we can break that kind of stuff up, we're pretty happy about that. So this looks pretty innocuous. It's not clear that this is such a useful or interesting thing. It is actually very powerful. A simple example would be you're at a party. There are n people, and each of them, they all throw their phones into a box. So all these n people throw their phones into a box, and then each person closes their eyes, reaches into the box, and takes out a phone. And we would like to know the expected number of people that happen to take out their own phone. So how do we analyze that? It sounds difficult, but it actually is not. And it works like this. We'll say, what is xi is going to be a Bernoulli random variable that indicates if the ith person gets their own phone. So you could just ask, what is the probability that you individually, if you're at this party, independent of what is, of course it depends on the other phones that other people have taken already, but we're not going to condition on that. We're going to pretend we don't know that information, which we wouldn't. So we'll just say, absent any other information, what is the probability that I will reach into this box and pull out my own phone? Well, it's 1 on n, right? Because I'm pulling out a phone, and there's n of them. And so there's a 1 in n probability that I will take it out, the one that belongs to me. So each person has a probability of 1 on n of getting their own phone. So what is the expected number of people who get their own phone? Well, it's the expected value of the sum of these Bernoulli random variables, right? It's because it's the sum of how many people got their correct phone. So that's expected value of, oh, sorry, it's a little hard to read there. Linearity of expectation, that's expected value of x1, summed through expected value of xn, and expected value of each one of these is 1 on n. And so therefore, what you end up with is n times 1 on n, which is 1. So therefore, the expected number of people that happen to take out their own phone is 1. Let's try another example that shows how powerful this is. You're walking along a trail, and each minute you do one of 3 things. So let's say this is you right now. You're in this space here. You're this little dot. And each minute, one of 3 things will happen with probability 1/2. You're going to move forward 6 meters. So 1/2 probability. You're going to move forward 6 meters. With probability 1/3, you're not going to move at all. And so I'll make it 1/3. And then with probability 1/6, you move backward 2 meters. 1/6, you move backward 2 meters. Did I get those right? Yeah. And the question is, what is the expected position from where you started after an hour? So every minute you do one of these 3 things I described. The 1/2 probability that you move 6 meters to the right, a 1/6 probability that you move 2 meters to the left, and then a 1/3 probability that you just hold still. So what is the expected position from where you started after an hour? So an hour is 60 minutes. And so how could we write this? Well, the way I would think about this is I would say that the distance that you've moved, or the position, I would write this as, so your position, which is random, right? Because it depends on these random movements here. But that position, we're going to write that as being x1 sum through x60, right? Because it's just the sum of all these movements that you do, have those accumulate. And each xi represents the amount that you move at minute I. And so what do you have? You have x sub I it's a discrete random variable, and it takes on either the value 6 or 0 or minus 2, right? So x sub I is a discrete random variable, and it's either 6 or 0 or minus 2 with the probabilities 1/2, 1/3, and 1/6 respectively. So what is the expected value of xi? Well, it's 1/2 times 6 plus 1/3 times 0 plus 1/6 times minus 2, which is 8 on 3. Okay, 8/3. So expected value of xi is 8/3. And so therefore, what is my expected position? Well, my expected value of x1 summed through x60 is just expected value of x1 summed through expected value of x60. That's just 60 times 8/3, which is 160 meters. So your expected position is 160 meters to the right. We'll do one more example here. I'm not sure if people still do this, but cereal boxes used to have toys in them. After you finished all the cereal, you'd stick your hand in and you'd dig out some, goofy trinket or something in the bottom. Each box of your favorite cereal has one of 6 prizes in it, equally likely, and you want to collect all these prizes. So what is the expected number of boxes that you need to buy? So that's going to be our question, right? Obviously you need to buy at least 6 because you need to have 6 boxes, but you probably need to buy a lot more. This is a tricky one. This is not an easy question by any means. It requires quite a bit of thought. I'm just going to show you the answer because that's how you learn this stuff. You want to collect all the prizes. You're going to go to the store. You're going to keep buying more and more cereal boxes until you've accumulated all of them. So the way to think about this is the following. Let's say you just keep opening all the boxes and you write down the number of the prize that you get. So the first prize you get is number 3, the second one you get is number 2, the third one you get is number 4. So by this point you're pretty happy. You've opened 3 boxes and gotten 3 prizes, so you're pretty content with that. But then you get a 2 and a 3 and a 2 again. You go, okay, well, the 6 boxes that I've opened and I've still only gotten 3 prizes. But then you get number 5, so now you've got 4 prizes, and then 3 and 1. And then 1 comes up, so that's the 5th one, and now you're almost all set. You just need number 6, and so you open up several more, and then finally you get that number 6 at, I don't know how many boxes that was, but it looks like about 3, 2, 4, 2, 3, 2, 5, 3, 1, 4, 3, 2, 1, 6. So it's 14 boxes to get all those prizes in that example I just gave. So how do we attack this in a probabilistic way? Let's take those outcomes, take those prizes, and let's group them into segments, each of which ends in a new prize, right? So what I've done down here, I'm erasing all this stuff there. I'm taking the same numbers that I wrote up there, 3, 2, 4, 2, 3, 2, 3, 2, 4, 2, 3, 2. Those same numbers I'm writing here, but now I'm grouping them into segments where each segment ends on a new prize. Okay, so there's the first 3 segments just have length 1 because you got a new prize right off the bat. And then the 4th segment has a length of 4 because it took you 4 attempts to get the prize. The 5th segment has a length of 2. It took you only 2 attempts to get a prize after that. And then 5 length for the last one. So I've grouped these into segments of this length. And this question asks for the expected value of the length of the first segment. So sorry, I should say x1 is going to be the length of the first segment, x2 will be the length of the second segment, x3 will be the length of the third, and so on and so forth. And this question asks me for the expected sum of the lengths of these segments, right? It's asking me what is the expected sum of all these lengths here, of these x's. And so that's just the expected value of the length of the first segment plus the expected value of the length of the second, and so on and so forth, up to the length of the sixth segment. Sorry. So obviously, what is true? The expected value of the length of xi for each one of these segments. What is the expected length? Well, obviously, x1 has a length of 1 because the first box you open has a prize in it. So x1 is always 1. There's nothing random there. But each of these remaining xi's is a geometric random variable, and the success probability is 7 minus I on 6. So what do I mean by this? Let me erase some of those chicken scratches there. So we just said that x1 is equal to 1. The first segment has length 1 because the very first box of cereal that you get has a prize, and that's a prize that you get. So you've accumulated that. Okay. Now let's suppose you've gotten that first box and set it aside. So now what are you doing? Now you want to get the next box that is different from the box you just took, right? You want the next box that is different from the box that you just took. Well, what is the probability that the next box is new? It's 5 on 6, right? It's a 5/6 chance of having a new prize there. And so what is the random variable that describes the number of boxes that I need to select before I get a new prize? It's a geometric random variable. Remember, a geometric random variable is the number of attempts until you see your first success. So it's a geometric random variable, and the success probability is 5/6. Okay, and then once I've gotten that second prize, now I'm dealing with a geometric random variable with a success probability of a 4 on 6, right? Where does 4 on 6 come from? It's because I've already taken 2 prizes, and now there's 4 new ones I'm looking for, so 4 on 6. And so on and so forth down to 3 on 6, 2 on 6, and 1 on 6. So a geometric random variable with success probability p, it turns out the expected value of a geometric random variable with success probability p, the expected value is 1 on p. Okay, that's you'll see that in a table later, but that is what the expected value of a geometric random variable is, and therefore the expected length of all these segments will be 1 plus 6 on 5 plus 6 on 4 plus 6 on 3, and so on and so forth. Work those numbers out, you get 14.7. So that's what that is. That's how we computed that. In general, this quantity here, this summation, the sum from I equals 1 to n of 1 on I, is called the nth harmonic number. And for large n, it looks like a log of n. So basically, log of n is how many attempts you need to make for like n boxes of cereal. A nice example of this would be if you wanted to know how many people you'd have to be friends with in order to have a friend on every single day of the year. So in other words, you want all 365 days of the year covered. That's an exact analogy with this example we just gave, right? Instead of boxes of cereal with prizes, instead of 6 prizes, you have 365 prizes, and you're going out and meeting people. This same kind of logic dictates that if you wanted to make friends, so you had one friend with a birthday on every day of the year, you would need to look at about 2,153 according to this logarithmic approximation. The actual amount, though, would be 2,364. So if you have like 2,300 friends, then on the average you have one friend for it's someone's birthday on any given day. So you have a lot of cake to eat.